Planets hide everywhere in our galaxy. They orbit nearly every star you see at night, yet humans discovered exactly 0 of them until 1995. The problem isn't that planets are rare. The problem is that finding them requires solving the hardest puzzle in astronomy. Tonight we're exploring the ingenious tricks astronomers invented to catch invisible worlds. You'll discover how the tiniest wobbles expose giant planets. Before we begin, drop a comment about what you think makes planet hunting so impossible. If you enjoy these space detective stories, consider subscribing. Stars completely outshine their planets. This creates astronomy's most impossible challenge. Even Jupiter would vanish next to any star. Imagine hunting for a firefly. Now place that firefly right next to a blazing searchlight. Try spotting it from across an entire city. That firefly represents Jupiter. The searchlight represents our sun. For decades, astronomers aimed powerful telescopes at nearby stars. They found nothing. Stellar glare washed out everything. The brightness difference crushes any hope of seeing planets directly. This cosmic hide-and-seek forced scientists to abandon looking for planets themselves. Instead, they learned to catch planets through the tiny effects these invisible worlds create. Distance creates another crushing problem. Stars appear as tiny points of light even through our most powerful telescopes. This happens because stars sit incredibly far away from Earth. When you look at a star, you see a single dot. Any planets orbiting that star would appear right next to that same dot. Your eye can't separate two objects that sit so close together in the sky. Think of car headlights on a distant highway at night. From far away, both headlights blend into one bright spot. You can't tell there are actually two separate lights. Even the closest stars to Earth suffer from this same problem. The angular separation between a star and its planet appears smaller than what any telescope can resolve. This forces astronomers to develop completely different hunting strategies. Every planet tugs on its star as it orbits. This gravitational pull makes the star wobble slightly back and forth. That wobble shifts starlight toward different colors as the star moves. Scientists call this the Doppler effect. It's the same thing that changes ambulance siren pitch. When the ambulance approaches, the pitch sounds higher. When it moves away, the pitch drops lower. Precise instruments can detect these color shifts in starlight. The measurements require incredible sensitivity. Astronomers must catch stellar motion slower than walking speed. This breakthrough transformed planet hunting from impossible to systematic. Scientists stopped trying to see planets directly. They learned to read the gravitational stories that planets write in starlight itself. Sometimes planets cross directly in front of their stars. When this happens, the planet blocks a tiny amount of starlight. This creates a brief dimming that astronomers can measure. Picture holding a coin between your eye and a bright lamp. The coin blocks some light and creates a shadow. Planets do the same thing when they pass in front of their stars. The amount of dimming tells astronomers how big the planet is. Bigger planets block more light. Smaller planets create shallower dips. The timing between dips reveals how long the planet takes to complete one orbit. This method works only when planets cross exactly between Earth and their star. Most planets never line up this way, but when they do, astronomers can measure both planetary size and orbital period with remarkable precision. Massive objects actually bend light as it travels through space. This effect, called gravitational lensing, can reveal planets in a completely unexpected way. Einstein first predicted this bizarre phenomenon. When a star with planets passes in front of a more distant background star, gravity acts like a natural magnifying glass. The foreground star's gravity bends and focuses light from the background star. Any planets orbiting the foreground star create additional bending effects. These show up as brief spikes of extra brightness in the background starlight. Each spike reveals the presence of another planet. This method can detect planets that no other technique can find. It works across vast distances and can spot planets floating freely in space without any host star at all. Hunting for planets demands measuring the teeniest possible changes. The signals that reveal planets sit at the very edge of what current technology can detect. Any instrument noise drowns out planetary signatures. Ground-based telescopes face constant interference from Earth's atmosphere. Air currents blur starlight. Temperature changes shift instrument readings. Weather patterns introduce false signals. Space telescopes avoid atmospheric problems but face their own challenges. Solar radiation damages sensitive detectors. Thermal expansion shifts optical components. Cosmic rays create spurious readings. Modern planet hunting requires instruments stable enough to detect changes smaller than 1 part in 100,000. This precision pushes engineering to its absolute limits. Many astronomical phenomena can mimic planetary signals. This creates a constant problem of false positives that fool even experienced astronomers. Binary star systems often masquerade as planetary detections. When 2 stars orbit each other, they create Doppler shifts identical to those from planets. Stellar spots rotating across star surfaces can mimic planetary transits. Instrumental glitches sometimes generate perfectly periodic signals. Confirming real planets requires multiple independent measurements. Astronomers must verify signals using different telescopes and different detection methods. They analyze stellar spectra for signs of stellar activity. This verification process often takes months or years. Many exciting discoveries turn out to be false alarms. Only the most rigorously tested detections earn recognition as genuine planets. Digital cameras revolutionized astronomical detection capabilities. These electronic sensors, called CCD sensors, can measure light with incredible precision. They replaced photographic plates that astronomers used for over a century. Modern spectrographs split starlight into thousands of individual colors. They can detect wavelength shifts smaller than the width of an atom. These instruments require temperature control to within thousandths of a degree. Computer processing power enables analysis of massive datasets. Automated algorithms search through millions of stellar measurements. Pattern recognition software identifies potential planetary signals. Without these technological advances, planet hunting would remain completely impossible. The combination of sensitive detectors and powerful computers finally gave astronomers the tools they needed. Individual stars rarely reveal their planets, but observing thousands of stars simultaneously increases the odds dramatically. This statistical approach transformed planet hunting from lucky accidents into systematic surveys. Large telescopes now monitor tens of thousands of stars continuously. Automated systems flag any unusual brightness changes. Computer algorithms sort through the data looking for repeating patterns. Even if only 1 star in 100 has a detectable planet, monitoring thousands of stars guarantees multiple discoveries. The Kepler Space Telescope observed over 150,000 stars for 4 years straight. This mass production approach has revealed that planets exist around most stars in our galaxy. Statistical analysis suggests billions of planets wait to be discovered. Earth's atmosphere constantly interferes with precise astronomical measurements. Air turbulence blurs stellar images. Atmospheric absorption blocks certain wavelengths of light. Weather patterns introduce unpredictable changes. Space telescopes escape these problems completely. They can observe continuously without weather delays. Their instruments remain stable without atmospheric turbulence. They detect wavelengths that never reach Earth's surface. The Hubble Space Telescope demonstrated the power of space-based observations. Its steady view of the universe enabled discoveries impossible from the ground. Later space telescopes specialized in planet hunting. Modern space missions like Kepler and TESS have discovered thousands of planets. Their success proves that space-based planet hunting represents the future of astronomical discovery. Planet discoveries have shattered every expectation about how planetary systems form. The first planets found around other stars were nothing like anything in our solar system. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths represent a planetary type that doesn't exist in our solar system. These worlds are larger than Earth but smaller than Neptune. They appear to be the most common type of planet in our galaxy. Some planets have highly elliptical orbits that would freeze and bake them alternately. Others are tidally locked with permanent day and night sides. Scientists have found planets with glass rain and diamond snow. This incredible diversity proves that our solar system represents just one possible arrangement of planets. The universe contains planetary architectures that stretch far beyond human imagination. Solar eclipses create some of nature's most spectacular displays. The moon slides in front of the sun. Daylight dims to an eerie twilight. The sun's bright disk vanishes behind the moon's shadow. Planets create their own version of this celestial show. They pass directly in front of their host stars. From Earth's perspective, the planet appears as a dark silhouette crossing the stellar surface. This planetary eclipse works exactly like a solar eclipse, but on a much smaller scale. The planet blocks a tiny fraction of starlight during its passage. Sensitive instruments can detect this brief dimming, even when the planet itself remains completely invisible. Astronomers call this event a transit. It transforms an invisible planet into a detectable shadow that reveals the planet's presence with mathematical precision. The dimming pattern tells a complete story about the orbiting planet. Astronomers plot this brightness change over time. The result resembles a shallow valley carved into an otherwise flat line. This brightness graph is called a light curve. It captures every detail of the planet's passage across its star. The depth of the valley reveals planetary size. The width shows how long the crossing takes. The light curve acts like a planetary fingerprint. No two planets create identical dimming patterns. Large planets carve deep valleys. Small planets create barely detectable dips. Reading these stellar stories requires incredible precision. But once astronomers master this technique, they can extract detailed information about worlds they'll never see directly. You might expect larger planets to block more starlight. This intuition proves correct. But the relationship follows a precise mathematical rule that amplifies small differences dramatically. The amount of dimming depends on the planet's area compared to the star's area. But area grows as the square of diameter. Double a planet's size, and it blocks 4 times more light. This squared relationship makes transit detection surprisingly sensitive to planetary size. A planet twice Earth's diameter creates a signal 4 times stronger. This mathematical amplification helps astronomers detect planets much smaller than Jupiter. The math works in reverse too. Measuring the exact dimming depth allows astronomers to calculate planetary diameter with remarkable accuracy. Transit timing reveals how fast planets travel around their stars. The duration of each transit depends entirely on the planet's orbital speed and the star's diameter. Planets in tight orbits race across their stellar disks quickly. Distant planets take much longer to complete their crossing. This timing difference acts like a cosmic speedometer. Combining transit duration with the known size of the host star reveals the planet's orbital distance. Faster transits indicate closer orbits. Longer crossings suggest more distant planetary paths. This timing method works so precisely that astronomers can map entire planetary systems. Each planet's orbital highway becomes visible through nothing more than careful stopwatch measurements. Planets must line up perfectly between Earth and their star to create visible transits. This geometric requirement eliminates most planets from detection. The orbital plane must align within less than 1 degree of our line of sight. Picture trying to see a person walking in front of a distant streetlight. You only see their silhouette if they pass directly between you and the light. Step slightly to either side, and the person becomes invisible against the background. Most planetary orbits tilt at random angles relative to Earth's viewpoint. These misaligned planets never cross their stellar disks from our perspective. They remain permanently hidden despite being perfectly normal worlds. Only about 1% of all planetary systems have the precise alignment needed for transit detection. This geometric lottery makes transits rare but extremely valuable when they occur. Real planets create transits that repeat with clockwork precision. Each time the planet completes one orbit, it crosses in front of its star again. This creates an unmistakable periodic pattern. The interval between transits reveals the planet's orbital period directly. A planet that transits every 10 days has a 10-day orbital period. Longer intervals indicate more distant orbits. This repetitive behavior distinguishes real planets from random instrumental glitches. False signals rarely repeat with such mathematical precision. Genuine planets never miss their scheduled appointments. Astronomers require at least 3 identical transits before confirming a planetary detection. This repetition rule eliminates most false positives and ensures reliable discoveries. The exact shape of a transit reveals subtle details about both the planet and its host star. The dimming doesn't happen instantly. Instead, it follows a precise curve as the planet gradually covers the stellar disk. The beginning of transit is called ingress. The planet starts crossing onto the star's edge. The ending is called egress. The planet finishes its journey across the stellar surface. These entry and exit phases create gentle slopes in the light curve rather than sharp edges. The slope steepness depends on how fast the planet moves and how large the star appears. Measuring these subtle curves allows astronomers to determine stellar sizes with incredible accuracy. The ingress and egress phases transform simple shadow measurements into precise stellar physics. Stars don't shine uniformly across their entire surface. The center appears brighter than the edges. This effect, called limb darkening, happens because we look through different amounts of stellar atmosphere. When you look at the star's center, you see deeper into the hot interior. Near the edges, you look through more atmospheric layers that absorb and scatter light. This creates a natural brightness gradient. Limb darkening affects every transit measurement. As the planet crosses from the star's bright center toward the dimmer edge, the amount of blocked light changes continuously. This stellar feature complicates transit analysis but provides additional information about both the star and planet. Astronomers must account for limb darkening to extract accurate planetary properties. Detecting small planets demands measuring brightness changes smaller than most instruments can reliably detect. An Earth-sized planet crossing a sun-like star dims the light by only 84 parts per million. That's like detecting the difference between a 100-watt light bulb and a 99.916-watt bulb from across a dark room. The precision required pushes current technology to its absolute limits. Ground-based telescopes struggle with atmospheric interference that creates brightness variations much larger than planetary signals. Space telescopes escape these problems but face their own stability challenges. Modern transit surveys achieve this extraordinary precision through careful instrument design and sophisticated data analysis. Even tiny planets leave detectable fingerprints when measured with sufficient accuracy. Many stars host multiple planets with different orbital periods. These planets can create overlapping transit signals that complicate the analysis significantly. Shorter period planets transit more frequently than distant ones. When two planets transit simultaneously, their combined dimming creates a deeper signal than either planet alone. Separating these overlapping events requires sophisticated mathematical techniques. Computer algorithms analyze the timing patterns to identify individual planetary contributions. Each planet maintains its own orbital schedule regardless of what other planets are doing. Systems with many transiting planets provide the richest scientific data. They reveal complete planetary architectures and allow detailed studies of how multiple worlds interact gravitationally. Planetary atmospheres absorb specific colors of starlight as the planet transits. This absorption creates tiny additional dips in the transit signal at particular wavelengths. Each atmospheric gas has its own absorption signature. Water vapor absorbs infrared light strongly. Sodium creates absorption in yellow wavelengths. Hydrogen produces features across multiple colors. These fingerprints reveal atmospheric composition. The technique works by comparing starlight during transit to starlight when the planet isn't blocking the star. Any extra absorption during transit must come from the planetary atmosphere. This atmospheric analysis transforms simple shadow measurements into detailed studies of alien world composition. Astronomers can literally taste the air of planets they'll never visit. Binary star systems often masquerade as transiting planets. When two stars orbit each other and one passes in front of the other, they create periodic dimming identical to planetary transits. Stellar spots rotating across star surfaces can mimic small planet transits. Large star spots temporarily dim the stellar surface as they rotate into view. These spots can persist for weeks or months. Instrumental problems sometimes generate perfectly periodic false signals. Electronic noise, thermal variations, and mechanical vibrations can all create convincing planetary mimics. Confirming real planets requires multiple independent observations using different telescopes and techniques. This verification process eliminates most imposters but demands patience and careful analysis from astronomers. Light changes color when its source moves toward or away from you. This fundamental physics principle happens everywhere in the universe. Ambulance sirens demonstrate the same effect with sound waves. When an ambulance races toward you, its siren sounds higher in pitch. As it speeds away, the pitch drops noticeably lower. Light behaves identically but shifts its color instead of pitch. Astronomers call this the Doppler effect. Moving stars shift their light toward blue when approaching Earth. They shift toward red when moving away. These color changes happen in precise, measurable amounts. Detecting stellar motion through color shifts requires splitting starlight into thousands of individual wavelengths. This technique, called Doppler spectroscopy, transforms tiny color changes into planetary detection tools. Gravity works both ways between stars and planets. Planets don't simply orbit motionless stars. Instead, both objects orbit around their shared center of mass. This creates a cosmic dance that reveals planetary presence. Picture two figure skaters holding hands and spinning. The heavier skater stays closer to the center. The lighter skater swings in a wider circle. Both skaters orbit around a point between them. Stars and planets behave exactly like these spinning skaters. The massive star barely wobbles around the center point. The lightweight planet swings through a much larger orbit. This wobbling motion makes the star alternately approach and recede from Earth. Each wobble cycle produces detectable color shifts that betray the hidden planet's gravitational influence. Planet mass directly controls how much the host star wobbles. Heavier planets create stronger gravitational tugs. These powerful tugs force larger stellar wobbles that produce bigger color shifts. A Jupiter-mass planet makes its star wobble at speeds of several meters per second. An Earth-mass planet creates wobbles slower than human walking pace. This dramatic difference determines which planets astronomers can find. Current instruments easily detect the vigorous wobbles from giant planets. Smaller planets create motion so subtle that only the most sensitive equipment can measure it. The relationship between planet mass and wobble strength explains why the first discovered planets were all giants. These massive worlds created the strongest signals that early instruments could reliably detect. Real planets create wobbles that repeat with perfect clockwork precision. Each time the planet completes one orbit, it tugs the star through one complete wobble cycle. This creates unmistakable periodic patterns. The wobble period reveals the planet's orbital period directly. A planet causing 10-day wobble cycles has a 10-day orbit. Longer wobble periods indicate more distant planetary orbits. These repeating patterns distinguish genuine planets from random instrumental noise. False signals rarely maintain mathematical precision over months or years of observation. Astronomers track stellar wobbles for multiple cycles before confirming planetary detections. This repetition requirement eliminates most false alarms and ensures reliable discoveries. Measuring stellar wobble speed allows astronomers to calculate planetary mass using precise mathematical formulas. Stronger wobbles indicate heavier planets. Weaker wobbles suggest lighter worlds. The calculation requires knowing the star's mass in the orbital period. With these values, the wobble amplitude reveals the minimum possible planetary mass. This mass determination works only in one direction. Astronomers measure how the planet affects the star, not how the star affects the planet. The result gives a lower limit rather than exact mass. The radial velocity method excels at weighing planets that transit cannot detect. It provides the missing mass information that completes our understanding of planetary characteristics. The shape of stellar wobble patterns reveals whether planets follow circular or elliptical orbits. Planets in circular orbits create smooth, sinusoidal wobble curves. Elliptical orbits produce distorted patterns. When a planet follows an elliptical path, it moves faster at some points and slower at others. This variable speed creates asymmetric wobble patterns that astronomers can analyze mathematically. The degree of pattern distortion indicates how stretched the planetary orbit appears. highly elliptical orbits create strongly skewed wobble signatures. This orbital analysis reveals that many exoplanets follow dramatically elongated paths, unlike anything in our solar system. These eccentric orbits provide clues about planetary formation and migration processes. Measuring stellar wobbles demands detecting speed changes smaller than human walking pace. The most precise instruments can measure stellar motion of just 1 meter per second. That's about 3 feet per second. This precision requirement pushes spectrograph design to extraordinary limits. Temperature changes can shift instrument readings by amounts larger than planetary signals. Mechanical vibrations introduce false wobbles. Modern spectrographs require temperature control to within thousandths of a degree. They use special chambers isolated from vibration and thermal variations. Some instruments compare starlight to laser frequency comms for ultimate precision. Achieving this measurement accuracy represents one of the greatest technical achievements in astronomy. It enables detection of Earth-mass planets around nearby stars. Stars themselves create wobbles that can masquerade as planetary signals. Stellar surfaces bubble and churn with convective motion. Magnetic activity creates spots and flares that affect stellar spectra. These stellar phenomena produce velocity variations that often exceed planetary wobble amplitudes. Separating real planetary signals from stellar noise requires sophisticated analysis techniques. Astronomers monitor multiple spectral lines simultaneously to identify stellar activity patterns. They track magnetic field variations and spot coverage across stellar surfaces. Statistical analysis helps distinguish periodic planetary signals from chaotic stellar variations. This noise reduction process often takes months of careful observation to complete successfully. Planets in distant orbits take years or decades to complete single orbital cycles. Detecting these worlds requires monitoring stars continuously for multiple orbital periods. A planet with a 10-year orbit demands at least 20 years of observation to confirm its periodic signal. Shorter observation periods cannot establish the repetition necessary for reliable detection. This time requirement explains why most discovered planets orbit close to their stars. These hot worlds complete orbits in days or weeks rather than years. Long-term surveys now monitor hundreds of stars for decades. These patient programs gradually reveal the distant, cooler planets that resemble our solar system's outer worlds. Many stars host multiple planets with different orbital periods and masses. Each planet contributes its own wobble signature to the combined stellar motion. Separating these overlapping signals requires advanced mathematical techniques. Computer algorithms analyze the composite wobble pattern to identify individual periodic components. Each planet maintains its distinct orbital signature regardless of other planetary influences. The process resembles picking out individual instrument sounds from a complex musical chord. Experienced astronomers can identify multiple planetary notes in the stellar symphony. Systems with many planets provide the richest scientific data. They reveal complete planetary architectures and allow detailed studies of gravitational interactions between multiple worlds. Einstein predicted something impossible about gravity and light. Massive objects actually bend light rays as they travel through space. This seemed like pure theory until astronomers began observing it everywhere. When light from a distant star passes close to a massive object, gravity curves the light path. The massive object acts like a natural lens. It focuses and amplifies the background starlight. This phenomenon is called gravitational lensing. It works exactly like a magnifying glass, but uses gravity instead of curved glass. Einstein called it one of his most beautiful predictions. The effect creates perfect natural telescopes scattered throughout our galaxy. These gravity lenses can reveal planets that no other detection method could ever find. Occasionally, astronomers notice a star becoming dramatically brighter over several weeks. The star can increase its light output by hundreds or thousands of times. Then it slowly fades back to normal brightness. This temporary brightening happens when one star passes almost directly in front of another more distant star. The foreground star's gravity acts as a lens. It magnifies light from the background star. From Earth's perspective, the background star appears to brighten smoothly. It reaches maximum brightness when the alignment becomes perfect. Then it dims as the foreground star continues its motion. These microlensing events occur randomly across the sky. They cannot be predicted or repeated. Each event provides a unique window into gravitational physics. Sometimes the smooth brightening pattern gets interrupted by additional spikes of light. These extra peaks last only hours or days. They indicate something smaller orbiting the lens star. Planets around the foreground star create these additional focusing effects. When the planet passes through the right position, it adds its own gravitational lensing. This creates a secondary brightness spike. The spike characteristics reveal planetary properties. Spike duration indicates planetary mass. Spike timing shows orbital position. Multiple spikes can reveal entire planetary systems. This planetary signature appears completely different from the smooth stellar lensing curve. The contrast makes planet detection surprisingly straightforward despite the complexity of the underlying physics. Each massive object creates a specific zone where its gravity can focus light effectively. Scientists call this the Einstein radius. It depends directly on the object's mass and distance from Earth. More massive objects create larger focus zones. Closer objects also produce bigger effective radii. These zones determine where planetary lensing effects become detectable. Planets must pass through their host star's focus zone to create detectable signals. The zone size controls how likely astronomers are observe planetary effects during each lensing event. Understanding Einstein radius calculations helps astronomers predict which types of planets they can detect through microlensing. It also explains why this method excels at finding specific planetary populations. Certain precise alignments between source star, lens star, and Earth create regions of enormous magnification. Astronomers call these high magnification zones caustics. They produce some of the most dramatic lensing events. When the background source star crosses a caustic region, its brightness can increase by factors of thousands. These events create sharp peaks in the light curves that last only hours. Planets near the lens star can create additional caustic structures. These planetary caustics produce brief but incredibly bright spikes that reveal planetary presence. Caustic crossings provide the most sensitive planetary detections possible through microlensing. They can reveal planets much smaller than Jupiter orbiting at various distances from their host stars. Microlensing events happen by pure chance. They require perfect alignment between three objects: the background source star, the foreground lens star, and Earth. These alignments occur randomly and never repeat. Once a lens star moves past the background source, the alignment breaks permanently. The same configuration will never occur again in human timescales. Each event represents a unique, unrepeatable experiment. This one-time nature creates both opportunities and challenges. It allows detection of planets that other methods cannot find. but it prevents follow-up observations using the same technique. Astronomers must capture all necessary data during the single occurrence of each event. Missing the brief planetary signal means losing the discovery forever. The galactic center direction contains the highest density of background stars in our sky. More potential source stars mean more frequent lensing events. This concentration effect dramatically improves discovery rates. Looking toward dense stellar fields increases the probability of favorable alignments. Surveys monitoring millions of stars simultaneously can detect dozens of lensing events each year. The galactic center provides an ideal target for large-scale microlensing surveys. Multiple telescopes monitor this region continuously during observing seasons. This directional strategy has revealed that lensing events occur much more frequently than early predictions suggested. The abundance of background sources makes systematic planetary detection feasible. Microlensing light curves contain intricate patterns that encode detailed information about the lens system. Extracting planetary parameters requires sophisticated mathematical modeling. Computer programs fit theoretical curves to observed brightness data. They test millions of different combinations of planetary mass, orbital distance, and geometric configuration. The fitting process can take weeks of intensive computation for complex events. Multiple planetary solutions sometimes provide equally good matches to the data. Advanced modeling techniques can determine not just planetary presence, but also precise masses and orbital distances. This mathematical analysis transforms raw brightness measurements into detailed planetary characterization. Microlensing provides information that other detection methods cannot obtain. It can measure absolute masses of both the host star and its planets. This happens through careful analysis of the lensing geometry. The duration of the lensing event reveals the lens star's mass. The planetary signal amplitude indicates the planet-to-star mass ratio. Combining these measurements gives individual masses. This mass determination works independently of stellar brightness or spectroscopic properties. It provides clean measurements uncontaminated by stellar activity or instrumental effects. The technique excels at characterizing planetary systems around dim stars that other methods struggle to study. It reveals planetary populations in distant regions of our galaxy. Some microlensing events show planetary signals without any accompanying stellar signature. These indicate planets floating freely through space without host stars. Astronomers call them rogue planets or free-floating planets. These wandering worlds probably formed around stars, but got ejected through gravitational interactions. They now drift through the galaxy as isolated objects. Rogue planets can only be detected through microlensing. They emit no light and have no host star to create wobbles or transits. Gravity lensing the only way to find these dark wanderers. The discovery of free-floating planets reveals that planetary ejection occurs commonly during system formation. Our galaxy may contain billions of these homeless worlds drifting in the darkness. Microlensing events happen unpredictably and last only weeks. Capturing planetary signals requires continuous monitoring from multiple locations around Earth. No single observatory can provide adequate coverage. International collaborations link telescopes across different continents. When one observatory faces daylight, another takes over the monitoring. This creates seamless 24-hour coverage of ongoing events. Alert networks instantly notify participating telescopes when promising events begin. Coordinated observations ensure that brief planetary signals don't get missed due to weather or technical problems. This global cooperation has transformed microlensing from a curiosity into a systematic planetary discovery method. The network approach maximizes the scientific return from each precious lensing event. Astronomers dream of photographing planets directly around other stars. This requires completely blocking the overwhelming light from the host star. Engineers developed a revolutionary instrument called a coronagraph to achieve this impossible task. A coronagraph works like creating an artificial solar eclipse. During a natural eclipse, the moon blocks the sun's bright disk. This reveals the faint solar corona that normally remains invisible. Stellar coronagraphs use precisely shaped masks or mirrors to block starlight. They create artificial eclipses that reveal the much fainter planets orbiting nearby. The technique requires blocking light with extraordinary precision. The challenge exceeds anything attempted in engineering before. Coronagraphs must eliminate stellar glare while preserving planetary light that appears billions of times dimmer than the star itself. Earth's atmosphere constantly blurs astronomical images. Hot and cold air pockets act like moving lenses that distort starlight. This atmospheric turbulence makes stars appear to twinkle and prevents sharp planetary images. Adaptive optics systems fight atmospheric distortion in real time. They use deformable mirrors that change shape hundreds of times per second. These mirrors counteract atmospheric turbulence as it occurs. A guide star provides a reference point for measuring atmospheric disturbances. Computer-controlled actuators bend the mirror surface to cancel out air turbulence effects. This creates images as sharp as if the telescope operated in space. Without adaptive optics, ground-based direct detection remains impossible. The technology transforms Earth-based telescopes into precision instruments capable of separating planets from nearby stellar glare. Stellar light creates false planetary signals called speckles when it interacts with telescope optics. These bright spots appear randomly around star images. They can easily fool astronomers into thinking they've discovered planets. Optical imperfections in mirrors and lenses scatter small amounts of starlight. This scattered light creates bright speckles that move and change over time. Some speckles persist long enough to mimic real planetary companions. Speckle suppression techniques help distinguish real planets from these optical artifacts. Advanced image processing algorithms track speckle motion patterns. Real planets orbit predictably while speckles move randomly. Modern direct detection requires sophisticated speckle control systems. These eliminate false signals that plagued early attempts at planetary photography. Young planets glow brightly in infrared light because they retain heat from their formation. This thermal radiation makes planets much easier to detect compared to visible light observations. The brightness difference between star and planet shrinks dramatically. In visible light, planets appear billions of times fainter than their stars. In infrared wavelengths, this ratio improves to merely millions to one. The reduced contrast makes direct detection significantly more achievable. Infrared observations require special detectors that can sense heat radiation. These instruments must be cooled to extremely low temperatures to prevent their own thermal emission from overwhelming planetary signals. Space-based infrared telescopes avoid atmospheric absorption that blocks many infrared wavelengths. This gives them a crucial advantage for thermal planet detection compared to ground-based facilities. Starlight has no preferred orientation when it travels through space. Scientists call this unpolarized light, but when starlight bounces off planetary surfaces, it becomes partially polarized. This creates a detectable difference. Polarization acts like invisible fingerprints that identify reflected light. Special filters can block unpolarized starlight while allowing polarized planetary light to pass through. This technique helps separate planets from stellar glare. The degree of polarization depends on planetary atmosphere and surface properties. Gas giants and rocky worlds create different polarization signatures. These differences provide information about planetary composition. Polarimetry offers a unique advantage for direct detection. It works independently of brightness differences and can reveal planets that other methods cannot detect. Planets must appear far enough from their stars to be resolved as separate objects. This angular separation depends on both the actual orbital distance and the distance from Earth to the star system. Even Jupiter would appear impossibly close to the Sun if our solar system were located at typical stellar distances. The required angular resolution pushes telescope capabilities to their absolute limits. Only the largest ground-based telescopes can achieve the resolution needed for direct detection. Space telescopes avoid atmospheric blurring, but face size constraints that limit their resolution. Current technology restricts direct detection to planets orbiting relatively nearby stars. More distant planetary systems remain beyond the reach of existing instruments. Newly formed planets shine much brighter than older worlds. They radiate tremendous heat energy left over from their gravitational collapse and formation. This makes them ideal targets for infrared detection systems. Young planets can appear thousands of times brighter than ancient, cooled planets. This brightness advantage overcomes many technical challenges that make older planet detection impossible. Planet-forming regions around young stars provide natural laboratories for direct detection. These stellar nurseries contain the brightest planetary targets available to current technology. The window for detecting young planets closes as they cool over millions of years. Astronomers must catch these worlds while they still glow brightly from formation energy. Direct detection enables detailed study of planetary atmospheres through spectroscopic analysis. When planetary light passes through spectrographs, it reveals the chemical fingerprints of atmospheric gases. Each gas absorbs specific wavelengths of light. Water vapor, carbon dioxide, methane, and other molecules create distinctive absorption patterns. These spectral lines identify atmospheric composition directly. Atmospheric spectroscopy works only when planets can be photographed separately from their stars. The technique requires actual planetary light rather than indirect detection signals. This chemical analysis represents the ultimate goal of planetary science. It provides direct information about habitability, weather patterns, and potential biosignatures in alien atmospheres. Real planets move in predictable orbital paths around their host stars. This motion distinguishes genuine planets from background stars or optical artifacts that appear stationary over time. Astronomers track suspected planets across multiple observations separated by months or years. Genuine planets follow curved paths that match gravitational orbital mechanics. Background objects show no orbital motion. Orbital motion analysis can determine planetary masses and distances using Kepler's laws. The combination of direct imaging and orbital tracking provides complete planetary characterization. This motion confirmation represents the gold standard for planetary detection. It eliminates virtually all false positive identifications that plague other detection methods. Future space telescopes will possess unprecedented capabilities for direct planetary detection. These missions combine coronagraph technology with space-based advantages to achieve breakthrough sensitivity. Starshade missions will fly large flower-shaped screens in space. These external coronagraphs will block starlight from distances of thousands of kilometers. The technique promises to reveal Earth-sized planets around nearby stars. Interferometry missions will link multiple space telescopes to create virtual instruments larger than any single telescope. This approach provides the resolution needed to separate closely spaced planets from their stars. These advanced missions aim to photograph potentially habitable worlds and analyze their atmospheres for signs of life. They represent humanity's first serious attempt to detect biosignatures around other stars. Stars appear fixed in their positions night after night, but extremely precise measurements reveal that some stars actually move in tiny circles against the background of more distant stars. This motion happens because invisible planets tug on their host stars. When a planet orbits its star, both objects actually revolve around their shared center point. The star performs a miniature dance in the sky. This stellar motion traces out a small ellipse over multiple years. The wobbling motion appears incredibly small from Earth's perspective. Even nearby stars shift by amounts smaller than the width of a human hair, viewed from several miles away. Detecting these motions requires the most precise position measurements ever attempted. This technique is called astrometry. It reveals planets by catching stars in the act of their gravitational dance with invisible companions. Modern astrometry demands measuring stellar positions to within microarcseconds. This unit represents an almost unimaginably small angle. 1 microarcsecond equals the apparent size of a dime viewed from a distance of 2,000 miles. Achieving this precision requires eliminating every possible source of measurement error. Atmospheric turbulence shifts stellar positions constantly. Thermal expansion changes telescope dimensions. Even tiny vibrations can ruin position measurements. Space-based astrometry avoids atmospheric interference completely. Orbiting telescopes can maintain the mechanical stability needed for microarcsecond precision. They operate in the vacuum of space where no air currents disturb their measurements. This extraordinary precision represents one of humanity's most ambitious technical achievements. It enables detection of planetary systems that no other method can reveal. The Gaia spacecraft has revolutionized stellar position measurement. This European Space Agency mission monitors over 1 billion stars simultaneously. It tracks their positions with precision never before achieved from space. Gaia operates from a gravitationally stable location far from Earth. The spacecraft measures stellar positions repeatedly over several years. This creates a detailed map of how stars move through space. Among the billion stars in Gaia's catalog, some show the telltale wobbling motion that indicates planetary companions. The mission's enormous sample size dramatically increases the chances of detecting these subtle movements. Gaia's systematic survey approach transforms astrometry from studying individual stars to analyzing entire stellar populations. This comprehensive dataset reveals planetary systems across vast regions of our galaxy. Astrometry provides the only way to measure true planetary masses without any geometric assumptions. Other detection methods give minimum masses or require estimating orbital orientations. Position measurements work regardless of how the orbit tilts relative to Earth. When astronomers measure stellar wobbles using Doppler spectroscopy, they see only motion along the line of sight. This provides incomplete information about the actual orbital motion. Astrometry captures the full wobbling pattern in 2 dimensions. The complete orbital motion reveals absolute planetary masses through direct application of Newton's laws. No statistical corrections or geometric assumptions are needed. The measurement gives exact values rather than lower limits. This capability makes astrometry invaluable for characterizing planetary systems discovered by other methods. It provides the missing information needed for complete planetary censuses. Neutron stars are collapsed stellar cores that spin at incredible rates while emitting beams of radio waves. These beams sweep across space like cosmic lighthouses. When the beam points toward Earth, radio telescopes detect brief pulses. Some neutron stars, called pulsars, maintain timing precision that rivals the best atomic clocks on Earth. Their pulses arrive with such regularity that astronomers can predict them years in advance. Any deviation from the expected schedule indicates external gravitational influences. Planets orbiting a pulsar cause tiny changes in pulse arrival times. As the pulsar wobbles due to planetary gravity, the pulses sometimes arrive slightly early or late. These timing variations reveal planetary companions. Pulsar timing provides a completely independent method for planetary detection. It works for stellar remnants where no other technique could possibly detect planets. Detecting planets around pulsars requires measuring pulse arrival times to within thousandths of a second. This demanding precision pushes radio astronomy technology to its limits. The measurements must account for signal delays caused by Earth's motion and interstellar medium. Each pulse carries a timestamp that astronomers compare to predicted arrival schedules. Differences smaller than a millisecond can indicate planetary perturbations. Systematic timing patterns reveal orbital characteristics. The gravitational effects of planets change pulse timing in predictable ways. Larger planets create bigger timing variations. Closer planets produce more frequent timing changes. Mathematical analysis converts these patterns into planetary parameters. This millisecond timing precision rivals the best laboratory instruments. It demonstrates the remarkable accuracy possible through careful astronomical observation. Binary star systems often eclipse each other as they orbit. These eclipses occur with clockwork regularity that astronomers can predict precisely. But sometimes the eclipses arrive earlier or later than scheduled. This timing variation indicates additional gravitational influences. When a third body orbits the binary system, it causes the entire binary to wobble slightly. This wobbling motion changes the light travel time between the binary system and Earth. The eclipses appear to speed up and slow down periodically. Eclipse timing variation reveals planets or other companions orbiting binary star systems. The technique works even when the companions are too small or distant to detect through any other method. This timing analysis transforms regular eclipse observations into sensitive planetary detection tools. It expands the search for planets to include complex multiple star systems. When multiple planets orbit the same star, they occasionally line up and create enhanced gravitational interactions. These planetary alignments disrupt the otherwise clockwork precision of transit timing. The disruptions reveal the presence of additional planets. Single planets transit their stars with perfect regularity. But when other planets exist in the system, their gravitational tugs cause small timing variations. Transits sometimes occur minutes early or late compared to simple orbital predictions. Computer models can identify which planetary configurations produce observed timing variations. The analysis reveals masses and orbits of planets that never transit themselves. Hidden planets betray their presence through their gravitational influence on visible transiting worlds. This technique multiplies the scientific return from transit surveys. Each transiting planet becomes a probe that can detect its non-transiting neighbors. Planets in wide orbits take many years to complete single revolutions around their stars. Detecting these distant worlds requires tracking stellar motions for multiple orbital periods. This demands observational programs spanning decades. A planet with a 20-year orbit needs at least 40 years of position measurements to confirm its periodic motion. Shorter observation periods cannot establish the repetitive pattern necessary for reliable detection. Long-term astrometric programs now monitor hundreds of nearby stars continuously. These patient surveys gradually accumulate the data needed to reveal distant, slowly orbiting planets. The investment in time yields discoveries impossible through any other method. This long-term approach represents astronomy's commitment to systematic discovery. Some of the most important planetary finds require generational dedication to data collection. Absolute stellar positions change due to many effects unrelated to planetary companions. Earth's orbital motion, stellar proper motion, and instrumental drift all shift apparent stellar positions. Relative astrometry eliminates these complications by comparing target stars to nearby background references. Background stars lie so far away that they show no detectable motion over human timescales. They provide stable reference points against which to measure target star positions. Any motion of the target star relative to these references indicates real physical displacement. This differential measurement technique dramatically improves detection sensitivity. It removes most systematic errors that plague absolute position measurements. The background stars act like a fixed coordinate grid in the sky. Relative astrometry enables ground-based detection of stellar wobbles that would otherwise remain buried in instrumental noise. It brings precision space-based capabilities within reach of Earth-based telescopes. Future interferometry missions will link multiple space telescopes to create virtual instruments with enormous effective diameters. These telescope arrays will achieve angular resolution impossible for any single instrument. The technique combines light from widely separated telescopes. When multiple telescopes observe the same target simultaneously, computer processing can combine their signals. This creates the resolving power of a single telescope as large as the separation between the individual instruments. Kilometer-scale separations produce unprecedented precision. Space-based interferometry avoids atmospheric limitations that restrict ground-based telescope linking. The stable space environment allows precise measurement of tiny phase differences between telescopes. This enables astrometric precision beyond current capabilities. These future missions will detect Earth-sized planets around nearby stars through direct astrometric measurement. They represent the ultimate realization of position-based planetary detection. Space offers one crucial advantage that Earth-based telescopes cannot match. There's no weather in space, no clouds block observations, no atmospheric turbulence blurs stellar images. The Kepler Space Telescope exploited this advantage to revolutionize planetary discovery. Kepler launched with a simple but ambitious mission plan. It would monitor the same patch of sky continuously for years. The telescope tracked over 150,000 stars simultaneously, watching for the tiny brightness dips that reveal transiting planets. This marathon observation strategy required unprecedented dedication to a single sky region. Ground-based surveys moved between targets nightly. Kepler maintained laser focus on its chosen stellar field throughout its entire operational lifetime. The continuous monitoring approach transformed planet hunting from random discoveries into systematic surveys. Kepler's unwavering gaze revealed thousands of planetary candidates that brief observations would have missed completely. Traditional astronomical surveys jump between different targets each night. This observing strategy works well for studying individual objects, but misses periodic phenomena that require sustained observation. Planet transits demand a completely different approach. Transiting planets create brief dimming events that repeat with each orbital cycle. Detecting these patterns requires monitoring the same stars for multiple orbital periods. Random sampling cannot capture the repetitive signatures that confirm planetary existence. Kepler's field of view contained carefully selected stars optimized for transit detection. The mission avoided crowded stellar regions where neighboring stars would contaminate measurements. Each target star received dedicated, uninterrupted monitoring. This focused observation strategy maximized the probability of detecting planetary systems. By committing to long-term surveillance of specific targets, Kepler achieved discovery rates impossible through traditional survey methods. Not every brightness dip indicates a genuine planet. Binary star systems often masquerade as planetary transits. Instrumental glitches can create convincing but spurious signals. Kepler's massive dataset required sophisticated statistical analysis to separate real planets from imposters. Astronomers develop probability calculations that estimate the likelihood each candidate represents a genuine planet. These statistical tools consider stellar properties, signal characteristics, and instrumental effects. Only candidates with high confirmation probabilities earn recognition as validated planets. The statistical approach works because false positives rarely maintain the precise characteristics of real planetary systems. Binary stars create different signal shapes. Instrumental artifacts produce random rather than periodic patterns. This mathematical validation process transformed planet discovery from individual confirmations into population studies. Kepler revealed not just thousands of planets, but the statistical properties of planetary systems throughout our galaxy. Spacecraft failures often end missions prematurely. When Kepler lost critical pointing control systems, the mission appeared doomed. But engineers devised an ingenious solution that gave the telescope a second life. The recovery demonstrated remarkable adaptability. The K2 mission used solar radiation pressure to help stabilize the spacecraft. This innovative technique allowed Kepler to point at different sky regions sequentially. Though less precise than the original mission, K2 continued discovering planets. The extended mission strategy masked scientific return from a partially disabled spacecraft. Instead of abandoning the telescope, mission planners adapted observing programs to work within new constraints. K2 proved that creative engineering can salvage valuable science from compromised missions. The extension doubled Kepler's operational lifetime and contributed thousands of additional planetary discoveries. The TSS mission adopted a fundamentally different strategy from Kepler's deep stare approach. Instead of monitoring faint stars in one region, TSS surveys the entire sky while focusing on bright, nearby stars. This trade-off optimizes for different scientific goals. Bright stars enable detailed follow-up observations that faint targets cannot support. Ground-based telescopes can measure masses and atmospheric properties of planets around nearby bright stars. Distant faint stars remain beyond the reach of detailed characterization. TSS divides the sky into sectors that it observes sequentially. Each sector receives sustained monitoring for several weeks before the telescope moves to the next region. This approach provides all sky coverage while maintaining the time baseline needed for transit detection. The Bright Star strategy creates a catalog of well-characterized planetary systems accessible to future detailed studies. TESS discoveries become prime targets for atmospheric analysis and habitability assessment. The James Webb Space Telescope represents a quantum leap in space-based astronomy capabilities. Its enormous mirror and infrared sensitivity enable detailed study of planetary atmospheres discovered by transit surveys. Webb transforms planetary detections into atmospheric characterization. When planets transit their stars, stellar light filters through planetary atmospheres before reaching Earth. Different atmospheric gases absorb specific wavelengths of this transmitted light. Webb spectrographs can detect these absorption signatures with unprecedented precision. Water vapor, carbon dioxide, methane, and other molecules each create distinctive fingerprints in planetary spectra. By analyzing these patterns, astronomers can determine atmospheric composition, temperature structure, and even weather patterns on distant worlds. This atmospheric analysis capability represents the ultimate scientific goal of planetary detection programs. Webb provides the tools needed to study planetary environments in detail rather than simply confirming planetary existence. The Piotto mission will search specifically for Earth-sized planets orbiting within the habitable zones of stars similar to our Sun. This targeted approach focuses on the planetary systems most likely to support life as we know it. Previous surveys discovered many planets, but most orbit stars very different from our Sun or follow orbits unlike Earth's. Piotto will monitor Sun-like stars long enough to detect planets with Earth-like orbital periods. This requires observation campaigns lasting several years. Earth-Sun analog systems provide the best laboratories for studying potentially habitable worlds. These familiar stellar environments allow direct comparison with our own solar system's architecture and evolution. Piotto's specialized mission design prioritizes quality over quantity in planetary discovery. The mission aims to find the relatively rare systems that most closely resemble our solar system. The Roman Space Telescope will use gravitational microlensing to detect planets in wide orbits that other methods cannot find. These cold, distant worlds represent a largely unexplored population of planetary systems. Roman will provide our first systematic census of outer planetary regions. Microlensing excels at finding planets beyond the snow line where water freezes in planetary systems. These regions contain the ice and rock needed for forming gas giant cores. Roman will reveal how common Jupiter-like planets are throughout our galaxy. The mission will also attempt direct imaging of nearby young planetary systems. Advanced coronagraph technology will block stellar light to reveal orbiting planets directly. This combination of detection methods provides comprehensive planetary system characterization. Roman's wide-field survey approach will discover thousands of planets across vast regions of our galaxy. The mission will transform our understanding of planetary demographics and formation processes. Future space telescopes will achieve the ultimate goal of planetary science, directly photographing Earth-like planets and analyzing their atmospheres for signs of life. These missions, including Abebex and LUVO-OR, represent humanity's first serious attempt to detect life beyond Earth. These advanced observatories will combine enormous mirrors with revolutionary coronagraph technology. They will block stellar light with precision sufficient to reveal Earth-sized planets orbiting in habitable zones around nearby stars. Spectroscopic analysis of directly imaged planets will search for biosignature gases like oxygen and ozone. These atmospheric constituents could indicate the presence of photosynthetic life on distant worlds. The detection of biological activity around other stars would rank among the most profound discoveries in human history. These future missions carry the potential to answer the ancient question of whether life exists elsewhere in the universe. Coronagraph technology must eliminate stellar glare while preserving the incredibly faint light from nearby planets. Two main approaches promise to achieve this extraordinary capability: internal coronagraphs and external starshades. Internal coronagraphs use precisely shaped masks and mirrors inside the telescope to block stellar light. These instruments create artificial eclipses that reveal planetary companions. The technology requires controlling light scatter to levels never before achieved. Starshades operate as separate spacecraft that position themselves between the telescope and target star. These flower-shaped screens block starlight from thousands of kilometers away while allowing planetary light to pass unobstructed to the telescope. Both approaches push engineering to its absolute limits but promise revolutionary capabilities for planetary detection and characterization. These technologies will enable the direct study of potentially habitable worlds. Future interferometry missions will position multiple telescopes in space and link them electronically to create virtual instruments with enormous effective diameters. This approach provides angular resolution impossible for any single telescope regardless of size. Space-based interferometry avoids the atmospheric limitations that constrain ground-based telescope linking. The stable space environment allows precise measurement of light phase differences between widely separated instruments. Kilometer-scale telescope separations will achieve angular resolution sufficient to directly image Earth-sized planets around nearby stars. These missions will provide detailed maps of planetary surfaces and atmospheric dynamics. Interferometry represents the ultimate expression of space-based astronomy. These missions will combine multiple cutting-edge technologies to achieve unprecedented observational capabilities. Modern planetary surveys generate datasets too large for human analysis. Machine learning algorithms now identify planetary candidates automatically by recognizing the characteristic patterns that indicate transiting worlds. This computational approach accelerates discovery rates dramatically. Artificial intelligence systems can process millions of stellar light curves simultaneously. They identify subtle patterns that human observers might miss or take years to analyze manually. The algorithms improve continuously as they process more data. Neural networks trained on known planetary systems can recognize similar patterns in unexplored data. These systems excel at distinguishing real planetary signals from the various types of false positives that contaminate survey data. AI-driven discovery represents the future of planetary astronomy. As survey datasets continue growing exponentially, machine intelligence becomes essential for extracting scientific discoveries from the flood of observational data. Astronomers expected to find planetary systems resembling our solar system. They assumed gas giants would orbit far from their stars where ice could form. The first exoplanets shattered these expectations completely. Giant planets were discovered orbiting closer to their stars than Mercury orbits our Sun. These worlds, called hot Jupiters, experience surface temperatures hot enough to melt copper. They complete entire orbits in just days rather than years. Some circle their stars in less than 24 hours. Hot Jupiters challenged everything scientists thought they knew about planetary formation. Gas giants require large amounts of ice and rock to form their cores. But ice cannot exist close to stars where temperatures reach thousands of degrees. The discovery of hot Jupiters revealed that our solar system represents just one possible planetary architecture. The universe creates planetary arrangements that stretch far beyond human imagination. Planet discoveries revealed a completely new type of world that has no equivalent in our solar system. These planets are larger than Earth but smaller than Neptune. Astronomers call them super-Earths, though they might be nothing like Earth. Super-Earths appear to be the most common type of planet in our galaxy. They represent the missing link between rocky worlds like Earth and gas giants like Neptune. Our solar system lacks any planet in this size range. These intermediate-sized worlds could be rocky planets with thick atmospheres or mini-Neptunes with substantial gas envelopes. Current technology cannot determine their exact nature. They remain among the most mysterious planetary discoveries. The abundance of super-Earth suggests that our solar system's planetary size distribution is actually unusual. Most planetary systems contain worlds fundamentally different from anything we see locally. Our solar system's planets follow nearly circular paths around the Sun. This seemed like the natural way for planets to behave, but many exoplanets travel on highly elongated orbits that stretch and compress their distances from their stars dramatically. Planets on eccentric orbits experience extreme seasonal variations. They alternate between scorching heat and freezing cold as they swing close to and far from their stars. Some planets travel on paths so stretched that their closest approach brings them 10 times nearer than their farthest point. These elliptical highways create planetary climates unlike anything in our solar system. Planets experience rapid transitions between extreme seasons lasting weeks or months rather than the gradual seasonal changes Earth experiences. Eccentric orbits reveal that gravitational interactions can reshape planetary systems long after formation. The circular orbits in our solar system represent a special case of stability rather than the universal norm. Close-orbiting planets face a gravitational effect that locks their rotation to their orbital motion. This phenomenon, called tidal locking, forces the same hemisphere to always face the star. One side experiences permanent daylight while the other remains in eternal darkness. Tidal locking happens when the star's gravity becomes strong enough to overcome the planet's rotational energy. The gravitational pull gradually slows the planet's spin until it matches the orbital period. This creates a world with fixed day and night sides. Tidally locked planets develop extreme temperature differences between their hemispheres. The day side can reach temperatures hot enough to vaporize rock. The night side may be cold enough to freeze the atmosphere solid. This locked rotation creates atmospheric dynamics completely unlike Earth's weather patterns. Powerful winds transport heat from the day side toward the night side, creating complex circulation patterns across the planetary surface. Planetary atmospheres show incredible diversity that extends far beyond anything found in our solar system. Some planets have clouds made of molten glass or liquid metal. Others possess atmospheres so thick they create crushing pressures thousands of times greater than Earth's. Atmospheric analysis through transit spectroscopy reveals the chemical fingerprints of distant worlds. Water vapor, carbon monoxide, sodium, and exotic molecules create distinctive absorption patterns. Each planet displays a unique atmospheric signature. Some exoplanets have atmospheres dominated by hydrogen and helium like gas giants. Others show evidence of water clouds, methane hazes, or sulfur compounds. The chemical diversity reveals formation histories and current planetary conditions. These atmospheric studies transform abstract planetary detections into detailed environmental characterizations. They provide the closest thing to visiting these distant worlds that current technology can achieve. Many star systems contain multiple planets whose orbits influence each other through gravitational interactions. These planetary families create complex orbital relationships that maintain stability over billions of years. Some planets lock into resonant relationships where their orbital periods form simple mathematical ratios. Resonant systems show remarkable precision in their orbital timing. Two planets might complete exactly 3 orbits while their neighbor completes 2. This 3-to-2 resonance prevents close encounters that could destabilize the system. Gravitational interactions can also create chains of resonances linking 3 or more planets. These resonant chains represent some of the most dynamically complex planetary systems ever discovered. Multi-planet systems provide natural laboratories for studying gravitational dynamics and planetary formation. They reveal how planets migrate and settle into stable configurations during system evolution. Every star creates a habitable zone where temperatures allow liquid water to exist on planetary surfaces. This region lies neither too close nor too far from the star. Planets in this zone could potentially support life as we know it. The habitable zone's location depends on stellar brightness and temperature. Hot stars create habitable zones farther out. Cool stars have habitable zones closer in. The zone boundaries shift as stars evolve and change brightness over time. Astronomers have discovered dozens of planets orbiting within their star's habitable zone. These worlds represent the best candidates for finding environments suitable for life. They include both rocky planets and larger worlds that might have habitable moons. Finding planets in habitable zones doesn't guarantee they support life. Atmospheric composition, magnetic fields, and geological activity all influence planetary habitability beyond simple temperature considerations. Current planetary positions often differ dramatically from where they originally formed. Planets migrate through their systems due to gravitational interactions with gas disks, other planets, or stellar companions. This migration explains many puzzling aspects of planetary system architecture. Hot Jupiters likely formed beyond the snow line where ice could exist. They then spiraled inward through interaction with the gaseous disk surrounding their young star. This migration brought them to their current extreme orbits. Planetary migration can also scatter smaller planets into eccentric orbits or eject them from their systems entirely. These migration processes reshape entire planetary systems during their early evolution. Understanding planetary migration helps explain why our solar system's architecture differs from most discovered exoplanet systems. Migration may be the rule rather than the exception in planetary system evolution. Some exoplanets exist in environments so extreme they challenge our understanding of planetary physics. These worlds experience conditions that create weather patterns impossible anywhere in our solar system. They represent natural laboratories for extreme planetary science. Planets orbiting very close to their stars develop atmospheric dynamics driven by intense stellar radiation. Some worlds have atmospheres hot enough to rain liquid rock. Others experience winds traveling at thousands of miles per hour. Ultra-hot planets can have atmospheric temperatures exceeding 4,000 degrees Fahrenheit. At these extreme conditions, familiar molecules break apart into individual atoms. Metal vapor can condense into exotic cloud formations. These extreme environments test the limits of atmospheric physics and chemistry. They provide insights into planetary behavior under conditions that laboratory experiments cannot reproduce. Determining whether distant planets could support life requires analyzing multiple factors beyond simple temperature ranges. Atmospheric composition, stellar radiation, magnetic fields, and geological activity all influence planetary habitability. Scientists develop comprehensive assessment frameworks. Biosignature detection focuses on atmospheric gases that could indicate living processes. Oxygen combined with water vapor suggests possible photosynthesis. Other gas combinations might reveal different types of biological activity. Planetary mass and composition affect the ability to retain atmospheres suitable for life. Too small and the planet cannot hold onto its air. Too large and it might accumulate, crushing atmospheric pressures. Stellar environment plays a crucial role in habitability assessment. Quiet stars provide stable conditions for billions of years. Active stars bombard planets with harmful radiation that could strip away atmospheres. The search for life beyond Earth drives the development of increasingly sophisticated detection technologies. Future missions aim to identify potentially habitable worlds and analyze their atmospheres for definitive signs of biological activity. Next-generation space telescopes will directly photograph Earth-sized planets in habitable zones around nearby stars. These missions will measure atmospheric composition with unprecedented precision. They represent humanity's first serious attempt to detect extraterrestrial life. The discovery of life elsewhere would rank among the most profound achievements in human history. It would fundamentally change our understanding of biology, planetary science, and our place in the universe. These future explorations will determine whether life represents a rare cosmic accident or a common feature of planetary evolution. The answer will reshape humanity's perspective on the nature and prevalence of life throughout the galaxy.